as you know, he's from the Netherlands. He is a well-known technology leader in the AI and big data domain. He's also collecting vintage motorcycles, which he's repairing. And these motorcycles have no names. This is what he said. But I would like to ask from you a warm welcoming applause, a double applause, because he's doing for two, for Bas Geerdink with fast data, concepts, architecture, and technology.
Yeah, thank you very much. Hello, everybody. Welcome again to my second presentation of the day. And apologies, first of all, because I know you were looking forward to watching the presentation from Catherine. But unfortunately, she lost her voice and she cannot be here. So yeah, I'm the fill-in, so don't expect too much, please. And be gentle. But anyway, let's get to it. We're going to talk about fast data, or that is streaming, data analytics, data processing in real time, whatever you want to call it. And at the end, actually, I also introduced some extra slides here to tie it a bit in together with machine learning. But before that, I will want to explain a lot about the concepts and architecture of streaming analytics. Because if you do this, if you analyze data in real time, well, what is real time? It's never real time, but I'll leave you to the official pronunciation of that. But then you run into some challenges that are not so clear when you first encounter them, and that's what I want to show you today. Well, you know me already maybe a bit, so I'm going to skip this slide. I'm going to start with this nice definition of big data. Pretty old already, but still probably valid. What is big data? It is one of these three values, or V's of data: volume, variety, and velocity. And actually, big data is, people only think usually at the first V, the volume. And because that's the big data stack. And never so much about velocity, the fast data stack. So, but it's also classified as big data. So it can be that you have data coming in such a pace that it's too much to handle in like ordinary systems, in ordinary hardware, infrastructure, software. And that's why you want to do something special. For example, distribute your data so that you can do parallel data processing. Well, for volume, we have specialized databases for that. We have big data appliances and software again, like Spark and like Snowflake database, etc., etc. And yeah, that's getting more mature at the moment. BigQuery is very popular. So yeah, great. But streaming data is still a bit a second choice, and you don't come across it that often. But there is also dedicated technology and frameworks for that. So what kind of use case are we talking about? Well, some examples that are listed here. For example, in retail clickstream analysis. Right? So if you want to analyze the behavior of your customers in a retail website, for example, Amazon.com or so, yeah, you want to do that in real time, because what a customer is interested now is what matters. We don't care what he was shopping for yesterday. We want to know what he's interested in right now. Right? So analyzing his behavior on the website in real time, again, is what's interesting. Finance, if you are analyzing payment data in a bank, yeah, you want to do it in real time mostly, because then you want to find out, hey, what is this customer doing? Is there maybe, for example, a fraud case or not? Insurance, trend analysis, etc. Actionable insights, very hot topic actually at the moment. You want to give insights to people to take action, and you want to do it on their real-time data, hey, what they are doing now in your app or in your website or wherever. So, plenty of industries and use cases to choose from. And for all of these use cases, there is a kind of a generic pattern in 3 steps. First, it is the preparation of the raw data. Because what I mean with preparation is basically combining events. Because in a lot of these cases, one single event, so one single click from a customer, or one single page visit, or one single money transaction in a bank is not that interesting. What you're interested in is in the combination of other events in the past, maybe up until 1 hour ago or so, something like that. And we will have a detailed slide about that later because it's called windowing of your events. Then we do the transforming of the events, because if you're combining events, you also want to get a conclusion out of that. You want to aggregate them and want to detect a certain pattern. So, for example, seeing what a customer is shopping for at this moment, what kind of category of items he's looking for. And maybe you want to give a follow-up action for the customer that is, for example, predicted by a machine learning algorithm. And that's also the next step. And finally, you want to produce a follow-up action, also again in your stream, in real time, for a customer to do something. For example, click on the action is to present a banner that he can click to purchase something else, or the action can be actually blocking a transaction when you're doing fraud analysis. In an architecture diagram, this looks like this. The 3 main steps: detecting the pattern, determining the action, and producing the notification. And you can actually divide it into technology blocks that you can combine into one stream. And I'm not going to go into detail too much for this, but it's important to realize that you can connect these kind of streams together in one big stream to make it as fast as possible. Because this entire flow needs to happen maybe in 100 milliseconds or so. You want to be as fast responsive to the customer as possible. For example, in the shopping use case, if a customer clicks on a certain web page, you want to immediately on that same web page that he's just about to show, that's where you want to have the banner, where he can, where you give him a recommendation for a product, for example. So that is the challenge, of course. What kind of tools are available for this? Well, starting with the data stream storage, where you store your events, there's actually, I want to argue, one major technology for that, which is Kafka. That's absolutely the leading infrastructure for this. There's also, similar technologies, and some are cloud-based, some are open source, whatever. But Kafka is leading in this sense. So a lot of things are also compared to Kafka. For example, if you have PubSub, the Google framework, so how does that compare to Kafka, right? So that already shows how important Kafka is in this regard. For the data storage that is not in your stream, for example, for your customer data or your the other relevant data that you need to query, you need to have a really fast database available. It can be a feature store that I presented in my previous store, or it can be a fast cache of data, because you have to be able to query that data in real time again with a very low latency. So probably traditional database or so don't really work fast enough for you. So choose a quick database, for example, Aerospike or Cassandra or anything else with extremely low latency. Then the stream processing itself. So when events come in and you're analyzing them, you're windowing them, you are doing the analysis of that, you're determining the next best action, etc., etc. There are stream processing frameworks available for you. And most of them are open source, and some of them been adopted by the big vendors. The 2 leading ones at this moment are Spark and Flink. Spark, you might be familiar with from the big data, the batch data processing framework, where you actually distribute your data in data frames across your cluster. They also have a great streaming framework. It's called Spark Structured Streaming. But the one that I'm most fan of is Flink. It's another framework. It's completely independent from Spark, and they are a pure streaming framework. So if you want to have the best streaming tool, I think, in my opinion, in this moment in the market, Flink is a great choice. But on the other side, if you already have Spark, that's also fine to use. If you're already on Kafka and you have a Confluent stack, then Kafka Streams, another option, might also be a good choice for you. So it depends a bit. And then finally, for model scoring, so for the machine learning model, going back to our previous talk about ML ops, you probably also need a very low latency for your model. So your model needs to be scored also in real time, which means that going across a network to an API to get a prediction might be taking too long. That's why you need to actually serialize your model in your data stream as an in-memory option, as a function actually. And there's models for that. Two of them that I mentioned here, Onyx and PNML, are great for this purpose. And they can actually be used by data scientists to export them also to this format, intermediate format, so that you can actually build them in your stream and distribute them across your fast data cluster. So this is the tech stack. I presented this small architecture without any technology implications in it, but this is how this is represented by the company Confluent, which is a leading company in this case because they are the core contributors of Kafka, and they also have a great Flink integration at the moment. So you see, this is how this is done, right? You have a Kafka store for your events. You have a stream processing engine, for example, Flink, that does all the computation and all the analysis. And then you have incoming data that you consume from whatever source. Usually it's your app or your apps, your other microservices, your website, name it, or other data sources like databases. You can, for example, respond to table changes, those kind of things. And at the end, you have syncs. So that's basically writing data to a certain source again, or integrating them with your other apps and microservices. And same slide, but a bit more complicated in this sense, a bit more detail on which events you actually need and which you need to store, and with the technology options on the right side. Right, so how do you do this? I'm going to get into a bit more depth at this moment, so bear with me. First of all, what is streaming processing? How does that work? Because it's different than a batch job. I always said that. A batch job is something that you build. It's ready to be used. It's waiting there. Maybe in your Kubernetes or in Spark or whatever. And with a trigger like a click or a scheduled action, it starts running and it stops running. It starts and it stops. And stream processing is, of course, different. A stream doesn't have a stop. You can actually also turn it around and say that a batch job is the same as a stream, only it has a start and stopping point. But that makes it already a bit more difficult. It's an ever-running process. But the concept of it is a bit similar than when you're doing traditional big data in Spark. It's working with the concept of jobs. So you have a job that you deploy to a cluster, and that's how both Spark and Flink work. Only those jobs don't have a start and end point; they just run. So that makes it a bit more difficult to upgrade them and to replace them. But you can still think of it in the same conceptual way. Each job has a pattern, basically. What it does is consuming data from a certain source, what you just saw on the left side of the diagram. Then it's grouping the events. In most cases, I have to say, there's a few use cases that I have seen where there's no grouping. Every single event is just taken and analyzed and processed, and then there's something that's being done with that. But most of the time, that's not so interesting. So windowing is the common way to do this. Then within that window, if that window is finished, then that window, the data in that window, all the events in that window of time are calculated, aggregated, so they are combined, they are actually, and a sort of conclusion is drawn from that. For example, the window, if I have a window of time of 1 hour and my customer is shopping on my website, then I can determine, I can see, okay, he's been looking at these products, so he's interested in this kind of product with this price tag or so, and that's why I'm giving a recommendation for a product that falls into that category. Or if you are working in a bank and you're analyzing financial transactions, you say, okay, my window is like a day. So I'm combining all the events of one single customer of 1 day in the past until now. And I'm checking if it is reasonable that this customer makes these transactions. Because, for example, if I'm doing a payment now in Budapest here in a store or in a restaurant, but the next hour I'm making a payment in Amsterdam, and the next hour I'm making a payment in New York, that is impossible, right? I cannot do that as a customer. So combining these 3 events leads to the blocking of these transactions, because it's just not physically possible to travel around that quickly. Right. So that's the windowing and the aggregation of the window. And finally, of course, that leads to another event, another conclusion, the summary, the calculation that follows, and you sync that to a source. You actually, you give a notification to a customer, or you write a record to a table or something else. So a sync is also a typical term of the streaming world. Now you know what it is. We all do this in parallel, because this is one of the things that why we're actually having this talk. Because if it's just streaming data from a relatively small source, I can probably do it on my laptop or on a cloud computer or so. But for like a big website, there are so many events, millions of events maybe per second even. Think about Amazon, all the events, all the clicks, all the scroll actions, etc. that are happening there. You have to do it in parallel. So you have to distribute your data across your infrastructure. And you can configure this on 2 levels, on cluster level and on job level. Makes sense, huh? You can say, okay, I want to have a cluster of 1,000 machines, but within 1,000 machines, I'm deploying 20 jobs that all do kind of different things. They all analyze different data sources, and they all do different actions, etc. So my 100 machines that I have available are not always used for those 20 jobs that I have. I could configure that to be reasonable, to say, okay, this one job needs 10 machines. And another job, I can distribute the data across 20 machines, because I know that it requires heavy memory usage, for example, or it takes longer computation, or there's just much more data to process. So this is something you need to be aware of and configure. It's also it comes down to how much you want to spend, how much cost you have, etc. Right. So that's what we have, right? We have a data stream, we have a source, the website, for example. We nicely distribute our data in parallel, so we do parallel processing, we have a use case running, and then an event comes in. Wow. Then something else happens, which is new to people who are not used to streaming, usually. There's a few different timestamps that you have to be aware of, starting with the event that occurs at a certain time. That's probably the most important timestamp. So that is, for example, the exact time in milliseconds that a customer clicks on a web page, or the exact time that a payment is made. Just continuing with these 2 examples. But that travels a long way across the network. And there's a few things happening in between, like serialization, deserialization, until they arrive in your event streaming processing engine, like Flink. And that's the time we call the processing time. Sorry, the ingestion time. And the time that we actually process them is even still a very little while later, and we call that the processing time. So these three timestamps differ. So if you would just say, okay, I let my events come in, and if I just analyze them how they come in, right? Then things might not work as you expect, and things will go wrong because the order of things will differ. And that is because there's uncertainty in your network and in your infrastructure. There's always latency between, especially the event time and the processing time. And this happens, what will happen is that events will run out of order. So your events that are in a certain order will appear in a different order in your streaming engine. So that's why your timestamp or just analyzing the events in the order that they come in is a bad practice actually, because order of course matters. If you want to, if you do payment analysis, you want to know which order the payments come in, but also for click streams and other things. So remember that there's event time and processing time, and always, and the good streaming frameworks work with event time. They don't care about the processing time. They look at a certain timestamp in the event itself, which is the event time. It's just a field in your whatever JSON or so that you come in, and that is where your streaming analysis happens with. If you don't remember this anymore tomorrow or Sunday or whatever, if you're lying in the sun or whatever you're doing, think about Star Wars, because there is also a difference in the Star Wars movies, right? So the event time of the Star Wars movies is different from the order that we have seen them in the cinemas, right? We started with Star Wars 4, which was actually in the Star Wars universe, the fourth movie in line. So event time is the time where the actual events happened in the universe. That's the events that matter. And the processing time, it's just the time that we see them. Okay, we're going to continue with windowing, because now we have already, we set up our stream, we are consuming data, it's all parallelized, we're analyzing data in event time, and then we have to combine these events. Go back to the example where we have 3 events that arrive just about after each other. We want to combine them, to analyze them together. And what you first do is you want to create a bucket, a definite boundary for your events. It has a sort of a starting time and a stopping time, or a begin and end time. And within that window, if then you want to combine those events to make a decision about it. So this window can be considered a bucket of time. There's a few things that you can do. There's a few options how you want to window your data. Sliding, tumbling, or session windows are the 3 most important ones. So again, a choice that you have to make, right? There's no good or wrong. There's just what is available for your use case. What money do you want to spend in your infrastructure? All kind of important decisions. But these are your options. So if time flows from left to right, and the small circles with the numbers are the events themselves, you can structure them and analyze them in different types of buckets. The simplest one is just a tumbling window. So let's say I have a window of 1 hour. That means that my events that arrive from 1 o'clock to 2 o'clock, those are combined. And then I move on to the next window. That's the event from 2 o'clock to 3 o'clock. Simple, and nothing wrong with that. Yeah? But you realize, of course, that this is not really real-time processing. Because, you have to wait for the next hour to complete before you actually have a new analysis of your window. So a more common approach already is to have a sliding window. For example, I could say I am interested in an hour of data again, same as the tumbling window, but I don't want to analyze that every hour, but I want to analyze that, calculate this every minute. Well, okay, that's great, but it does mean that you have 60 windows running at the same time, which is perfectly fine. Eh? You can say I have in frameworks like Spark and Flink, this is just a matter of configuration. 2 lines of code. Hey, sliding window with 1 hour, with a time span of 1 hour, but with a slide of 1 minute. That Flink said, okay, sure, I'll do that. What Flink then does in memory is keeping track of all these windows, and if they finish, so after each minute, you get the calculation for that window. It will also mean, of course, that these events will belong to multiple windows. So each event will be stored in all these windows in memory, and they will also be part of the analysis for that window. And that's what you want, of course, because you say, okay, I'm, for example, interested in what a customer is doing in the past hour. Yeah, then that's what you want to slide forward in time. And the final one, probably the most interesting one, but also the most complicated one again, is a session window. And that is a time undefined window, so you don't give it a starting time and an end time, but you trigger an event and you complete an event based on data in the events itself. And that means that you can, and it's called a session window because, yeah, you can think about it like a session from people logging in and logging off, for example. And so in that window, what are you interested in? For example, you could say the session starts when my customer starts browsing a certain category of items on my website, and it finishes when it's going to another category. Maybe at that moment you want to say, hey, you looked previously at the new iPhone or so, but now you're looking at jeans or so. Are you still interested in the iPhone or so? Just thinking this up, but something like that could be interesting for you. And that is also possible. So you can actually define your windows by characteristics of the event itself. Right. There's some considerations for windows. Windows are very important in stream analysis. So I would consider you to pay some attention to that, because, yeah, first of all, you don't have boundaries there. You can make the windows as big as you want, and a sliding window with a small slide as you want. But it will have implications to your stream till the moment that it can lead to a crash, for example, because if you have a large window, that means that you have a lot of data that you consume and that you hold in memory. If I would define a clickstream window of a week, whatever, that means that for every customer, I am holding all the events in memory for a whole week, and that's quite a lot of data already. Multiply that by the number of customers that you have, and you probably have a memory issue. At the same time, if you have a sliding window, you keep the slide too short. That means more windows in the horizontal way, so to say, stacking up on top of each other, and that also means memory applications. You can also cache it across multiple windows. I'm not going to go into detail in that. But the final thing is important, because if you have a time-defined window, so a sliding window or a tumbling window, that means that you have to have a certain timestamp that evaluates, hey, now it is time to evaluate my window. Now I'm going to do the calculation for a customer, and I'm going to draw a conclusion out of this. But going back again to the slide with the event time, think about that slide again. There's always a bit of latency. You have to make a choice when to do that calculation. And when is that? That's actually not so easy to say. Because if you pick any time point, any point in time, there might still be an option that an event arrives in your streaming processing engine after your time that you picked. Because events can be late, they can be delayed. So if you say, for example, I have a window of 1 hour, doesn't mean if it's tumbling or sliding window. My window is 1 hour, and okay, I give it a bit of slack, so I'm doing the evaluation of that window. 1 second after the window has passed. So now it's 1 o'clock until 2 o'clock. So 1 second after 2 o'clock, I'm making the calculation for the entire window. But then what happens if 2 seconds after 2 o'clock, an event arrives with a timestamp of 1 second before 2 o'clock? Yeah, that's a bit strange, right? That event should have been evaluated in your window that you have just already completed. So that is the important decision point. How long do you give this amount of slack in your window to perform the calculation? How long do you still allow events to enter your window before you actually wrap it up and calculate it? Because events that will arrive later, yeah, you probably just have to ignore them. A solution for this is watermarks. So if you come across this, you also know what this is. So the watermarks are actually a timestamp that trigger the computation of the window. So what I just said, maybe give it 1 second of slack, then your watermark is 1 second after after an event arrives with a timestamp that should not have belonged to your previous window anymore. Right? So my window is from 1 o'clock to 2 o'clock. Then I get an event that is outside of that window, so probably the next window I started. But my watermark is 1 other second, then I'm waiting another second in my stream processing engine, and then I'm doing the calculation of the previous window. And that gives usually just enough room to make sure that 99% or so of all the events that you want to capture are in that window. If you then it's still an option that your infrastructure just doesn't allow just has too much latency, so an event is arrived even at a later time, then it's ignored. And in Flink, and there's now I think the most technical thing, the depth that we have in Flink, there is actually an option that's why this is an extremely sophisticated framework, and probably any use case can handle it. It's even possible to allow a property called allowed lateness that reprocesses the event in the unlikely case that an event still arrives after your watermark. So in that case, you could make a choice to recalculate the whole event and send a new follow-up action. But then you of course have to also be aware of that could happen in your stream, in your downstream API or database, whatever you use for that. Right. Another important topic in stream processing is the consistency of events. And maybe you've heard about this already, but there's a few semantics that you need to be aware of. And you have to pick one. Let's stick to that. At least once, at most once, or exactly once. Exactly once is the most complicated one, but also the thing that everybody wants. If I am doing streaming analysis in a bank for money transactions, I want to make sure that my events, my payments are processed exactly once, because they have an impact on customers, for example. But usually, the semantic of at least once, so guaranteeing that an event is always processed, but it could be more, is also good enough. That's, for example, in the case of clickstream analysis. If you just want to make sure that you're processing all your events, it doesn't really matter if you sometimes have a double event that you process twice. Yeah? So most of the tools that we have in stream analysis can guarantee at least once or at most once, and you can actually configure that. But there's a few combinations of technologies that guarantee exactly once. And again, going back to my infrastructure of Kafka and Flink, that's actually well suited for this. But nowadays, also Kafka and Spark structured streaming are capable of handling exactly once semantics. And why is that? How do they do that? Well, think about the events. They are somewhere in a source system. Then they are not processed in our streaming engine, right? They have not entered that. So in that situation, if they're not, they're somewhere still in Kafka, for example, then it's okay for us. They are there for us to be picked up. They are waiting to be consumed, actually. So we don't care about that too much, actually, because in the case, for example, that our stream breaks, that our event processing stops, we can just continue from where we have left off. Kafka works with the concept of offsets for this. So Kafka knows where its consumers have left off. They know, okay, hey, I've sent this data to this consumer, for example, my Flink environment, and hey, it suddenly stops for a few seconds or so. Oh, there it's back again. Then I'm giving my stream that data from where it's left off. So it's a great concept, actually. But the second stage, now let's take the first stage once. We have the processing of the event, and after that we send it out again to Kafka. It's Kafka in, Kafka out, right? To be picked up by the next stage. For example, my API. And again, that works the same. I'm offloading data to Kafka, which makes sure that it's persisted and can be picked up by the next handler. But there's also some data in between. And think about the windowing again. There's data that is in memory in my stream somewhere. I have picked it up. I am doing some analysis with this. Maybe I'm even doing a calculation with this already. I'm doing complex things like machine learning scoring. Or maybe I'm just windowing it and holding it in memory. What happens then if my stream breaks? If there's a huge crash in my infrastructure, or there's a data issue or so, and suddenly things fall apart. Then this data that was in memory is in transit. It will be lost somehow, right? In that case, the good streaming frameworks have a way of actually preserving that data, first of all in memory, so they keep cache in memory that is robust, and they also can offload this cache periodically or manually to disk, and that is extremely useful for stopping your stream. Because else, how can you preserve your windows? For example, the windows will be a day or an hour big or so. The data is all in memory, and now I'm releasing a new version of my streaming job. Now, what happens then? First, you make a backup of your state on disk. We call it a checkpoint. The checkpoint. Or manual action is called a save point. Then we can safely take our stream offline for a little bit. We reload the new job. We continue streaming again. And the first thing we do is reload the state from disk, so that all of the events that have been in transit before and were in memory, basically in our windows, are back again. Are again ready to be processed further. And so these kind of mechanisms guarantee exactly once processing, and it's not common in many frameworks. Okay, so this is the thing I just mentioned. Okay, we're almost out of time, but I did want to mention one more thing. It's about model scoring. So if you're doing machine learning analysis, for example, if you have a window of data and you want to draw a conclusion from that with a machine learning framework, you want to score a model. I already mentioned there's a few things you have to, you probably don't have enough time to go across a network and for every window or every event even, and call an API and wait for the results to come back from your model. What you actually want to do is distribute your model itself in a function across your entire data stream. And we have a few data solutions for that, a few cross-platform model formats for this. And this is just the model formats, but there's also frameworks for this, like open scoring, etc. You'll find it out if you Google this. But the popular ones are Onyx and PMML and maybe PFA. PMML is XML-based and PFA is JSON-based, but they're essentially the same. that allow you to export your model to something else that you will probably normally do, like JobLib or something else. But the good thing is that these are indeed cross-platform models. So they are independent of Python, for example. Also because Spark and Flink are Java-based frameworks. So usually you program against them with Java or Scala. Yeah, it's not so easy to make this change between a model that was developed in Python to your streaming processing engine, which runs in a Java environment. So luckily, there's intermediate formats for this, and they're extremely easy to use. So this little piece of source code shows the Python code for your model to train a small model, and with the command sklearn to PMML, I'm exporting my model to a PMML file, basically, which I then can load in memory and distribute across my streaming engine. And the PML file is just XML, and PFA is the same, but it's JSON. Okay, yeah, so basically we're at the end of the talk. Some alternative stacks maybe that you could consider, as I mentioned already, Flink is probably most advanced at this moment. Spark Structured Streaming is also really good, but you know, the companies like Microsoft and Amazon, of course, also want you to do streaming data analysis on their own platform. So they have tools available like Azure Streaming Analytics, in combination with Cosmos DB, or AWS Kinesis Data Firehose, in combination with DynamoDB. So yeah, whatever tool you like, you can pick. But some of them are more advanced than the others. Just to wrap up, I'll leave this here for reference, and I would like to thank you for your attention, and especially for listening in on this, yeah, sort of emergency talk. Thank you very much. And I hope it was it was on time.
we have time, like 2 minutes for questions. Yeah.
Okay, that's good.
It was a longer presentation. Okay, provocative question. In which order would you show the Star Wars series to newbies?
Well, actually, I am watching the series with my daughter, and I am actually watching them in processing time.
Mm-hmm. Okay.
So that means I started with part 4, if you remember correctly.
Okay. Let's jump on to more technical grounds. Using 4 different software packs for data stream storage, cache, stream processing, and model scoring seems inefficient. Is it possible to do this more efficiently?
4 different software packs for data stream. Yeah, yes. I know what you mean. So in the architecture that I showed, it's not on screen anymore, there is these different blocks for doing this. And yes, it's possible to combine them, but these stream processing frameworks are so efficient that it's usually worthwhile to also store the intermediate events. But if you want to, you can of course combine them into one package, depending on your requirements of latency. Yeah.
Okay, last question: how to process all events so to be complete, but at the same time provide timely answers, so late events are not waited forever?
How to process all events to be complete, but at the same time provide timely answers so late events are not waited forever. Yeah, there is no guarantee that you. I mean, late events. If you think about really late events, there's always an option that you miss them. There is just no 100% guarantee system that I can think of where this is a guarantee, except for doing maybe crazy things like putting the watermark one day ahead or so, but it doesn't really make any sense. So to do this, I'm thinking about this now. I think the only thing you can do is do some retro analysis, being aware that this is an option. Your events can be late. You can actually miss them. And what do you do in this case? You can say, okay, in this case, I'm maybe manually handling them or so, something like that.
Thank you very much. This was all. I have actually the picture of Catherine with us. So thanks a lot for being the best, Catherine, and being the true reinforcement of the Reinforce stage today. So another round of applause, please, for Bas Geerdink.